Hello everyone and welcome back to another video. Today I'm going to be trying to talk about something very complicated that I thought about and wrote about in my journal the other day. We'll see how this goes. I hope I can explain it pretty well. I thought I wrote about it decently, but here it goes. I'm going to be talking about the nature of time and how that like a sort of calculus analogy that relates to it. So for those of you who have a decent understanding of calculus, you'll get this, and even if you don't, I think I'll be able to explain it in a decent enough way where you could probably understand it. So this basically began when I was trying to think about things like change and how they relate to calculus and things like that. And I kind of began to think about some of Zeno's paradoxes, like the stuff related to motion and stuff related to infinity and all those sort of things. And then with motion, I began to think about time, because time is simply a measurement of motion. Because when you, like, the actual measurement for a second is how long it takes a certain thing to, like, oscillate back and forth. I don't know the exact specific. Go look it up. Go fact check me, please. I would like to be fact checked. Anything I say, please fact check it. I've said this in so many videos now, but go ahead, please fact check me, and if I get something wrong, put it in the comments, and I will correct it next time, and I'll probably, if it's bad enough, I'll put a correction in the comments. But that's my basic understanding of how time is measured. It's a measurement of motion. But either way, that doesn't really matter to my main point of it. One thing with time that confuses a lot of people is our observation is only of these single moments in time. All we do is take a screenshot, like that sort of thing, a screenshot of reality at a single moment, and there's no motion in that. It's simply a still picture. It doesn't move, it doesn't do anything, but we perceive motion because of all these different pictures that we take, in a sense. How does that work? How can there be motion if there's only specific instances in time, if there's only specific points? This issue has to do with the difference between our perception of time and the reality of time. There's not actually a major difference between these two. Our perception is still 100% valid, 100% correct. 100% is what we perceive is absolutely correct. We don't perceive everything, though, it's not actually an issue, though. That's the thing. It's similar to, this is where the calculus analogy comes in. So think about integration, which is finding the area under a curve for those people who don't know much about calculus. So like if you think about you have a graph, right? You have a graph, which is a graph of a function, which is simply a y value for every x value. But whatever, that doesn't really matter right now. You have a graph, right? And then you find the area under that graph, essentially, for those people who have no idea anything about math or who get turned off completely by it. I love math. That's kind of why I was writing about calculus in my journal, because I just really love math. But so you have the area underneath the graph. How do you measure that? Well, you can't just take there's no like specific area function for a curve. So basically what integration does is it draws a bunch of lines from the point on the graph to the x-axis, and it draws a line there, and then draws another line all the way across until you have all these lines lined up, and basically essentially creating a plane, which is just an area, a flat surface. And then you basically add up all those lines, and that's the area. Now what integration does is it basically makes it so that all these lines are infinitely thin, which means zero thinness, but also zero distance between all of them, and then it sums them all up. And that will give you the actual area. But to make it like an approximation, you basically do what's called a Riemann sum, where you take little lines that have really thin area, and then you just sum those up. And those, like, you have those are actually like rectangles, kind of. And you basically take all those rectangles underneath the thing and sum them up. But they're basically lines, because over time they become thinner and thinner and thinner and thinner and thinner, and there's no like sort of it doesn't follow the curve exactly, but as it approaches infinity, when the thickness becomes zero, it does follow the curve exactly. That's basically kind of how integration works. I tried to make it simple enough to understand. I hope I did. But for those of you who don't understand it, that's basically how it works. So when it comes to essentially with integration, what you're doing, you're taking these lines, which are one-dimensional, and you're making a two-dimensional plane from them. You're coming from one dimension to 2 dimensions, which is basically what a lot of calculus actually is, that because, differentiation, you're just making a line, and you're turning a whole line into a point that you can find the slope of, which the slope of a point doesn't actually make any sense, but it does in the context of calculus. But whatever, that's basically what a lot of what calculus is like making differentiation is making a higher dimension into a lower dimension, so like a line into a point, and then integration is turning all these lines into a plane. But that's a very crude simplification, but that's essentially what it is. So that is how you essentially switch dimensions in that sense, by taking an infinite amount of those things, and that switches the dimensions. But you also can switch dimensions by taking close to infinity, approaching infinity amount of, because you can never actually reach infinity, but you take a very large number of those individual lines, and that will also convert the same. There's a slight error, but that error is extremely small and still quantifiable. And the fact is, those individual lines are still valid. They're still true for what the function is. So, let's move on to the nature of time. So for time, you have all these individual points, all these individual moments that you observe. They're single points. They're zero-dimensional because they're points in time. But the actual nature of time is a one-dimensional timeline, essentially, when you think about it. That's what contains motion. That's what contains all those things. All the single points don't contain motion. They're simply a snapshot of a moment. Just like the lines are just a snapshot of the distance between the function and the x-axis. But the actual nature of the area under the curve, is a plane. But, so, what happens when you observe time, you observe all these specific little moments. And that's actually how your eyes work. They take little snapshots of each moment in time, and you perceive each moment. But there's a lot of these. It's like a very large number that is approaching infinity. So, you essentially, from these moments in time, by summing them up along this timeline, you get to the nature of time. That's how your perception of the nature of time. You don't actually perceive, because time would be infinitely small moments, and then every single infinitely small moment with no degree of separation between them. But what you perceive as time, you perceive these moments with somewhat of a separation between them, because you do have a finite mind. You can't perceive infinity. You can't perceive an infinite number of moments. That doesn't make any sense. And that's actually not what you do either. But what you do, you perceive a very large amount that approaches infinity, that gets very close. So this essentially means that there is a slight error, a very small error. But what you actually are doing, that's how you perceive time. That's how you see, that's how these moments become this line, how these points become a line. That's essentially what calculus has shown to us. But you do have a slight error, because it is an approximation of the actual nature of time, because it's these points with somewhat of a bit of space separating them. However, when you think about in calculus, you do have an error when you do these sort of calculations, but the error is so small, and you can almost always find an upper bound to that error. Plus, you know that every single point that you perceive, every single line that you have, is an actual fact about the function. Just like every single moment that you perceive is an actual fact about reality. And each of these moments, when they are put together, you don't have much to fill in these blanks. The blanks are very tiny. The error that there is so small, so imperceivable, that it really is ultimately meaningless in most contexts. In calc, there's also sometimes where you definitely need a little more precision too. But that's what we create. That's what science is, essentially. That's what we create, all these small instruments that detect all these little things. That, honestly, thinking, this is speculation, but this honestly might be why it's so hard for us to think about like those tiny increments of time when it comes to things like quantum physics and all the quantum shit that's really confusing and shit. This might be why it's so difficult for us, because we don't have the ability to perceive such things at such precision because of the nature of how we perceive time. We perceive the specific moments that ultimately are summed up and formed into this timeline, but we don't have that infinite precision that we would need to perceive the quantum realm in like this time in the quantum realm perfectly. So I think then in that sense it does make sense why it's so difficult for us to perceive the quantum stuff. But I mean, that simply means that we need to improve our science, and we need to improve our precision for viewing time, and view more moments out of the actual fact of the timeline, perceive more moments out of that, so that we can come to knowledge of what the fuck is going on in the quantum realm, because we know very fucking little about quantum physics right now. It's all like probabilistic, and there's nothing like certain, which means that we have a lot of work to do, I think. And I think that's speculation, but that might be some sort of insight, might sort of help you understand some of the stuff related to quantum physics right now. But yeah, I think that's all I have to say for today. Thank you guys for watching, and I hope to see you in the next video. Peace.